This lecture continues the examples involving gravitational potential energy in its Newtonian form. Let's immediately take a look at the next example, copy it down into your notes. Let's do a little bit of black hole physics. The problem is as follows. Calculate the Schwarzschild radius of a black hole. How large would the radius be for a black hole with a mass of the Earth? What about the supermassive black hole at the center of the Milky Way, which is 3.5 million solar masses? Okay, now think of a black hole as two things. Okay, the first thing is what is called the singularity. A singularity is literally a point of infinite density. It is a point of finite mass, but it is of literally zero size. Therefore, if density is mass divided by volume, this then means that this is a point of infinite density. Okay, now how does a singularity form? A singularity forms from the deaths of extremely massive stars. Okay, let's begin, however, this process by examining the sun. Right now, the sun is in a state of what is called hydrostatic equilibrium. There are two forces basically being exerted upon the sun that are canceling each other out. We have, first of all, the sun's inward pull of its own gravity. This literally wants to cause the sun to collapse upon itself. Okay, what prevents that, however, from happening? Well, nuclear fusion is occurring in the core of the sun right now. Hydrogen is fusing into helium, and then therefore there is a pressure that is exerted outwards from the core of the sun. This cancels out the inward pull of gravity, and then therefore the sun remains in this state of hydrostatic equilibrium. As long as there is hydrogen fuel that is present in the core for the nuclear fusion reactions to occur, this state will then persist. This state, by the way, corresponds to what is called the main sequence portion of the sun's lifetime. Okay, in the case of the sun, right now the sun is about halfway or so through its main sequence lifetime. Right now the sun is about 5 billion years old. However, eventually gravity will win the game. The reason for that is because the nuclear fusion, which is persisting in the core of the sun right now, will eventually begin to shut down as the hydrogen fuel is depleted. So as the hydrogen fuel is depleted, what then happens? Well, the sun will begin to collapse upon itself. As it begins to collapse upon itself, that inward pull of gravity actually heats up the core of the sun to a hotter temperature. When this happens for a brief period of a few million years, it's hot enough in the core of the sun for helium to fuse into heavier elements, specifically carbon, nitrogen, and oxygen. When this process happens, there is an enormous pressure that is exerted outwards within the sun itself. This then causes the sun's outer atmosphere to balloon outwards, and as it does, it cools down and then therefore turns red. This is referred to as the red giant phase of the sun. This state will persist for a few million years. And then after that, due to some pretty complicated physics, the following happens. An enormous solar wind is generated within the atmosphere of the sun, and it actually begins to puff off the sun's outer atmosphere such that it forms a nebula. This type of cloud or nebula is referred to as a planetary nebula. The reason for that is because the first examples of these types of objects that were seen in telescopes in the 19th century resembled planets. So unfortunately, even though these objects have nothing to do with planets, they are referred to as planetary nebulas for this reason. Okay, then what happens with the core of the sun that is left over? Once again, some pretty complicated physics here occurs as nuclear fusion begins to shut down in the core, but basically you end up with all of these atoms, if you will, of carbon, nitrogen, and oxygen, all crammed together as tightly as they can be. This is referred to as a state, by the way, of quantum degeneracy. The object itself that is left over is not undergoing nuclear fusion, but it's still extremely hot, and it begins to lose energy slowly over time. The core that is left over in this process is about the size of the Earth, and it's referred to as a white dwarf. So eventually this is what will happen to the sun. It will eventually become a planetary nebula as the outer atmosphere is puffed off outwards, and the core of the sun will eventually cool off as a white dwarf. If you give this process enough time, eventually the white dwarf will cool down to a point where it radiates no light at all. It basically then becomes a black crystal, if you will, of carbon, nitrogen, and oxygen. This is referred to as a black dwarf. There are actually no black dwarfs in the universe right now, and the reason for that is because literally not enough time has elapsed in the universe for black dwarfs to form. But this is eventually what will happen to the sun. Okay, now if you have a star that is more massive than the sun, however, gravity wins the game, but it does so in a different way. In the case of very massive stars, you begin once again with nuclear fusion in the core of the star. Hydrogen is fusing into helium, and then eventually the nuclear fusion shuts down. The star begins to collapse upon itself, which then causes the helium to fuse into heavier elements, carbon, nitrogen, and oxygen. Eventually, that nuclear fusion will shut down, and because the star is large enough, as it begins to collapse upon itself, it then heats up that core of carbon, nitrogen, and oxygen to the point where it can actually fuse into heavier elements. So what you end up with is you end up with kind of like this alternating pattern of nuclear fusion, gravitational collapse, and nuclear fusion again with increasingly heavier and heavier elements in the case of a very massive star. Eventually you work your way up the periodic table in this manner to iron. Iron is extremely stable as a nucleus, and it's extremely hard to fuse. In the case of a star will not literally generate enough heat in its core for iron to fuse into heavier elements. This is when gravity wins the game. So what you end up with is this enormous core of iron at the center of this star, and nuclear fusion has shut down. And then just over the course of minutes, it turns out, then at that point, the star's atmosphere basically collapses upon itself. And as it collapses upon itself, it rebounds off the core, which is being crushed in this manner. And as the atmosphere rebounds off the core, this then results in an enormous explosion called a supernova explosion. The supernova explosion is so energetic that basically everything past iron on the periodic table can now form by the process of nuclear fusion. This cannot happen, however, while the star is in a state of hydrostatic equilibrium. What happens to the core itself? The core is literally crushed down, in the case of a very massive star, to a point. That point is an object of finite mass, several times the mass of the sun, but of infinite density. That is a point of zero size, and that is what is called a singularity. A medium mass star, by the way, something, say, less massive than what I've just described, undergoes the same sort of process, the supernova explosion and so on and so forth, but it eventually crushes the core down to a point where you end up with basically a ball of neutrons. A ball of neutrons that won't collapse all the way down to a single point, but is instead forming what is called a neutron star. A neutron star is an object that is basically a big ball of neutrons, and it's a few times more massive than the sun, and it's about the size of a city. So a neutron star is kind of like this weird example that occurs between what will eventually happen to the sun with a white dwarf and so on, and what happens when you form a black hole. So the first part of a black hole is the singularity, and it forms in this manner. Okay, now what is the second part of a black hole? Well, that's this that I'm drawing here, and what I'm drawing here is not a structure. It's instead a horizon, and this is sometimes referred to as the event horizon. And the distance that it is from the singularity is referred to as the Schwarzschild radius, which I'm going to write here as capital R sub S. Now, what is the event horizon? Well, think of it like this. Think of it in terms of escape velocity. Let's say that you're an observer that is over here somewhere, and you're looking at the black hole. Let's say that an object is right here. It's further from the singularity than the event horizon. This then means that the escape velocity of this object is less than the speed of light. So then therefore you would be able to receive information from that object, you would be able to see it. However, if you take that object and you put it here, say closer to the singularity than the event horizon, then the escape velocity at this distance from the singularity is literally greater than the speed of light. So then therefore you would not be able to receive any information from this point right here. You would not be able to see this object. Therefore, at this distance right here, at the Schwarzschild radius, at this distance right here, this is then where the escape velocity is equal to the speed of light c for an object, say, of mass m. So then therefore, what would you see if you were over here and you looked in this direction? You would be seeing a horizon. You would be seeing a perfectly featureless black sphere, but you're not looking at a structure when you look at it. Instead, you're looking at a horizon, a point beyond which you can't see for this reason. So now what we're going to do is we're going to do an escape velocity calculation, and the unknown in this expression is going to be r sub s, which is called the Schwarzschild radius. It's named after the mathematician Karl Schwarzschild, who early in the 20th century, working with general relativity, derived the expression that we're about to explore. We're going to derive it, however, just classically by using conservation of energy. So we're going to set up an escape velocity calculation, and by the way, the mass of the black hole itself here will have some mass I'm going to refer to as m hole. And then we're going to set up an escape velocity calculation where the object will start here with the speed of light as its escape velocity, and it then therefore ends up infinitely far away like so with a speed of 0. Okay, so once we understand that, then we just fill in our terms. 0 equals delta k plus delta u, and then we just plug in the following. Okay, so first of all, the final kinetic energy is 0. The object ends up at rest, and now watch this. The initial kinetic energy occurs here, where our speed is equal to the speed of light. Like so. And there it is, for the first time in this course, mc squared. You're going to see it again much later on. Okay, now changes in gravitational potential energy. We end up infinitely far away, so the final gravitational potential energy is 0. And then minus the initial at this distance here from the singularity. The singularity, of course, is our origin. Just be careful of the negative signs. So negative g, mass of the black hole, mass of the object over r sub s, like so. And now what we do is we just solve for r sub s. So let's go ahead and cancel the negative signs here, like so. Let's take this term and move it to the other side. Like so. Okay, let's go ahead now, oops, this is r sub s. And now let's go ahead and cancel out the mass m, here and here. And then let's go ahead and cross multiply all this stuff over and r sub s, and let's solve for r sub s. When we do, we end up with a very famous equation. It appears on t-shirts involving black hole physics. Okay, so the Schwarzschild radius is then therefore the following. Oops, this is the mass of the black hole, excuse me. Like so, and then divided by c squared. Okay, now let's go ahead and calculate what this is for a couple of simple scenarios or situations. Okay, first of all, we have our numbers. Capital G, of course, is as follows. Okay, and then the speed of light c is also a fundamental constant. It will become very important, by the way, near the end of this class, near the end of this course, and that's 3 times 10 to the 8th meters per second. And now let's call part A here. What happens if you could somehow crush the Earth to the point where it becomes a singularity, where its mass is 6 times 10 to the 24 kilograms. So imagine taking the Earth somehow and crushing it down to a single point. In other words, it undergoes gravitational collapse and it becomes a singularity. If we can somehow turn the Earth into a black hole, what would then its Schwarzschild radius be? So that's what we're asked to solve for here in what I'm calling part A of the example. So let's just plug everything in, where the mass of the hole now is the mass of the Earth. Okay, so the value of the Schwarzschild radius, let me get my calculator, is as follows. So 2 times g, then times the mass of the black hole, which is the mass of the Earth in this case, and then divided by c squared. So plugging that in as well. And then ultimately you end up here with about 0.009 meters. That's 9 millimeters. That's about a centimeter. So imagine, for example, that we crush the Earth into a black hole, and then it's, say, somewhere here in this room. If it was here in this room, by the way, we would have some serious problems, but that's another story. And then what you would see here in this room, for example, is this perfectly featureless black sphere with a diameter of about 2 centimeters. It would basically look, say, something like this. And you would be so tempted to reach out and grab it. However, don't do so, because if you go beyond the event horizon, you're never coming back. You're not going to be able to pull your hand back, because in order for you to be able to do so, you would have to have an escape velocity that is greater than the speed of light. So don't reach out and grab that black hole, because if you do, you are never coming back. Okay, now let's take a look at a more realistic situation, and that's the supermassive black hole that resides at the center of the Milky Way. The supermassive black hole at the center of the Milky Way has a mass that is 3.5 million solar masses. Remember, we have explored this in a previous example. Okay, so I'm going to call this part B. Okay, so in part B, the mass of the black hole is going to be 3.5 times 10 to the 6 That's 3.5 million multiplied by the mass of the sun. Okay, the mass of the sun, let me write that over here. Once again, we've seen this number before, is 2 times 10 to the 30th kilograms. So let's go ahead and find this number here first for the mass of the black hole. So 3.5 times 10 to the 6th, and then 2 times 10 to the 30th for the mass of the sun. There we go. And that comes out to be 7 times 10 to the 36 kilograms. Okay, so using that number now, let's go ahead and figure out what the Schwarzschild radius is for this actual black hole. Okay, so I've got the mass of the black hole here on my calculator, and then multiply that by g, like so, and then multiply by 2, and then divide by c squared. So after doing the math, you end up with about 1.04 or so times 10 to the 10th meters. So that's obviously pretty big, but it's actually smaller than an astronomical unit. If I divide out by 1.5 times 10 to the 11th meters, that's what an astronomical unit is, then I end up here with about 0.07 or so AU, which is still fairly large. Okay, now recall the supermassive black hole that's at the center of the galaxy M87. That black hole has actually been photographed. It's been photographed by using radio light, for example, and we have actually directly seen the event horizon of that black hole. That black hole is so enormous in terms of its mass that its event horizon has a Schwarzschild radius that is larger than the solar system. Okay, that concludes this portion of the lecture here.